You hear a lot about AI in medicine, right? But how do we actually know if an algorithm is any good? I mean, how do you grade a machine on something as complex as reading a medical scan? Well, today, that's exactly what we're going to do. We're putting an AI to the test, grading its performance against a trained human expert. Let's see how it stacks up. Right, so how do you give a computer a medical exam? It's not like it can take a multiple choice test. We need an objective way to measure its performance, a hard number that tells us, yep, it passed, or nope, back to the drawing board. And that's where this whole challenge gets really fascinating. Okay, first things first. Before we can grade the AI, we need an answer key, don't we? A perfect score to aim for. In the world of medical imaging, that perfect answer comes from a human expert. This is our gold standard. So take a look here. On the left, a standard chest x-ray. But what you really want to see is on the right. That clean white shape, that is what we call the ground truth. A real human radiologist has carefully and precisely outlined the lungs. That is the perfect answer we're looking for. That's the target. And that brings us to the core challenge. Can we get a machine to look at that raw x-ray and automatically generate the exact same mask with no human help at all? Just the algorithm doing its thing. That's the whole game. Now, you can't just throw the raw image at the computer and hope for the best. That would be like trying to read a book in a dark room with smudged glasses. First, we have to prep the image. We need to clean it up so the computer can actually see what it's supposed to be looking at. We do this with a two-step process. First up is a technique called CLHE, which enhances the contrast and makes all the details pop. Then, and this is the part that sounds a little weird, we apply something called a Gaussian blur. I know what you're thinking. Why would you blur an image you want to analyze? But stick with me, because this step is absolutely crucial for getting an accurate result. And you can see the effect right here. We start with the original image, then, in the middle, that's after we boost the contrast with CLHE. Much clearer, right? And finally, on the right is the Gaussian blur. See how it just gently smooths out the image? It gets rid of all that distracting, pixel-level noise, which lets the algorithm focus on the real edges of the lungs, not just some random static. All right, our image is prepped and ready to go. Now it's time for the algorithm to take its shot. We're using a classic computer vision technique for this, called the Watershed Algorithm. It has a really clever way of seeing the image that's perfect for this kind of task. So think of it like this. The algorithm doesn't see a flat picture. It sees a 3D landscape, where the brightness of each pixel is its height. Then it starts to flood this landscape from its lowest points, or basins. As the virtual water level rises from different basins, the floodwaters eventually meet. And those lines where they meet, those become the boundaries. Pretty smart, huh? This shot here shows you the whole shebang, from start to finish. You can see the original image on the far left, and as we move to the right, you see it get processed, refined, and cleaned up step by step. Each panel is one more move toward the final goal, until there it is on the far right. That's the AI's final answer, its attempt at creating the lung mask. So the AI has turned in its homework. Now for the moment of truth. We can't just eyeball it and say, yeah, that looks about right. We need an objective mathematical score. We need the judge's scorecard. And for that, we use the Dice score. In medical image segmentation, this is the go-to metric. Its entire job is to measure how much the AI's prediction overlaps with the expert's ground truth. It's great because it equally punishes the AI for coloring outside the lines and for missing spots, which gives us a really balanced view of its performance. Now, don't let the formula intimidate you. The concept is actually really simple. It's all about agreement. It basically takes the area where the two masks overlap, doubles it, and then divides that by the total area of both masks combined. It's just a precise mathematical way of asking, how similar are these two shapes? And the scoring couldn't be simpler. A score of 1.0 means a perfect match, flawless. A score of 0.0 means there was zero overlap at all, a total miss. Everything else just falls somewhere on that scale. It's a clean, simple way to grade the machine. So, how did our AI do? It's time for the final verdict. Let's compare its work to the experts and see the score. And here it is, the side-by-side. On the left, in blue, you have the AI's prediction. On the right, in green, is the human expert's ground truth. You know, at a glance, it's not bad. It got the general shape down. But if you look closely, especially around the bottom edges, where the lungs meet the diaphragm, you can see it's not quite perfect. That's a really tricky area to get right. This difference map gives us an even clearer picture. Think of it like a visual report card. The green areas are where the AI got it right, a perfect match. The red bits are where it got a little too enthusiastic and colored outside the lines. And the blue areas are the spots it missed completely. It's a crystal clear breakdown of its strengths and weaknesses. So, what's the final score? The AI earned a DICE score of 0.5559. So what does that mean? Well, it's a solid C+. It tells us the algorithm is on the right track. It correctly identified over half of the lung area. But it's also clear that it's not ready to replace a human radiologist just yet. There's still plenty of room for improvement. But a score like this isn't an ending. It's a benchmark. It tells us where we are right now. The next logical step is to bring in more advanced algorithms, maybe some deep learning models, and see if we can push that score much, much closer to a perfect 1.0. Which leads to the really big question. What will it take to teach a machine not just to see shapes, but to truly understand what it's looking at, just like a human expert does?